So welcome back, everyone. Hope everyone had a good break. Scary news from Gavin Newsom today, right? About what can happen with shelter-in-place orders. So please do stay safe, everyone, as the prediction of cases continues to go up. I don't know what that means for the laboratory. Jonathan, do we know what that means for the laboratory? If we go below these 15% ICU beds, we're going to shut down the lab?
That's what I imagine, yeah, except for essential personnel.
Yeah, so you basically got, for a payer, you got a week to get whatever sample you need to in the fridge before we all sit at home. But anyway, that's unofficial thought, right? No official word on that yet, but do be careful with this and do take care of yourselves. That being said, it is a pleasure to have a presentation today entitled Measuring the Capabilities of Quantum Computers, to be given by our guest from Sandia National Laboratories, Dr. Timothy Proctor, who is a staff scientist in the Quantum Performance Laboratory, QPL, at Sandia National Laboratories, where he researches techniques for performance assessment and enhancement of current and future quantum computers. Tim studied theoretical physics at the University of Leeds in the United Kingdom, where he also obtained a PhD in physics under the supervision of Dr. Viv Kendon. During his PhD, Tim spent a year visiting Professor Brigitte Whaley's group at UC Berkeley, after which he joined Sandia's QPL as a postdoctoral researcher. Since becoming a staff scientist, Tim has led the QPL's quantum computer benchmarking research. So please join me in welcoming Tim to give today's presentation. Please go ahead, Tim.
Thanks very much. So yes, I'm going to be telling you about some work we've done on measuring the capabilities of quantum computers. This has been work with the whole team at the Quantum Performance Lab, which is Kenny, Kevin, Eric, and Robin. There we go. So this work is about answering a really high-level question in quantum computing, which is that if someone says that maybe you want to buy their quantum computer, or want to spend some of your valuable research time on that quantum computer, what everyone really wants to know is what can I do with that device? And in particular, lots of people want to know what applications or algorithms can I run on that device? So there's many different things you might want to do. Perhaps you want to run random circuit sampling and get a splashy Nature paper demonstrating quantum supremacy. You might want to run, say, quantum error correction. Perhaps you want to demonstrate a logical qubit or test out your new quantum error correction code. Or you might want to run some kind of NISQ algorithm, such as QAOA or VQE. Perhaps you want to try out one of the building block quantum circuits, such as like phase estimation or the quantum Fourier transform. So there's loads of different things researchers want to try on quantum computers, and these all have different characteristics. And there's really no good way currently of answering the question of whether a device can run these applications. And so this talk is really about new techniques that we think are a decent step towards answering these questions. It's certainly not the answer. There's a lot of work to do before we could give you a really comprehensive answer to this kind of question. We think it's a nice step in that direction. So as I've said, we're trying to measure the capabilities of a quantum computer. I really need to start by telling you what I mean by capability. And so ultimately, as I said in the previous slide, you're going to measure this in terms of its ability to run a useful algorithm. Just as if you're, say, buying a laptop, you might want to know whether it can run the latest version of Pro Tools or your favorite video editing software, whatever kind of thing you're into. And the problem is that this depends on really too many unknowns right now for quantum computers. For example, we don't necessarily know what algorithms we want to run. Those might not even exist yet. This is a very active area of development. We don't really know which are the best algorithms to actually run on quantum computers. But even if you did know that, there's still a lot of unknowns here. So for example, how do you actually run that algorithm on the device? How do you compile it into native operations? There's many different aspects to this, such as you can trade off the depth of a circuit with the width of a circuit. You can also improve how you actually do the compiling onto the specific device you have. This is all active areas of research as well. Are you using logical qubits or not to encode this algorithm? Or maybe it's a NISQ algorithm, and maybe this has special purpose error mitigation, so actually you can do a lot better than it looks like you're doing because there's some clever data analysis technique to remove a lot of the noise in the results. And then finally, there's the question of what even constitutes success for an algorithm. This is going to depend from algorithm to algorithm. Perhaps you're trying to beat a particular classical algorithm. Perhaps you need to get to a specific accuracy. And so all of these complex questions are really, really interesting, but they're all kind of research questions in their own right. We're not really ready to deal with all of this all together. So for now, what we've done is we've defined a quantum computer's capability as the set of quantum circuits it can run with high probability of success. And that's because a quantum circuit is a much more concrete object than an algorithm. Quantum circuit is the kind of thing you see in a textbook, where you have these wires that correspond to the number of qubits, and then there are layers of logic operations. So there'll be D layers, and in each layer, there's some gates applied to the qubits. And so these are reasonably concrete objects. There's still a bunch of complexity here, lots of subtleties, but they're a lot more manageable than if we're talking about algorithms. And for the purposes of this talk, we're going to be able to mostly ignore all of those subtleties. So now I've told you that what we mean by capability is what circuits a device can run. You might think that that is just fixed by a device's error rate. So I think everyone's probably seen these kind of high-level talks where somebody has one of these plots with the number of qubits along one axis and then something like 1 over the average error rate on the other axis. And then each device is just a point on one of these plots. So for example, the red quantum computer here has less qubits, but it has a lower average error rate. And then this the blue one here has more qubits, but higher error. And so for one of these plots to really mean anything, to really actually tell you much about the device at all, there's really an implicit error model going on here. And that is that an error occurs with a probability of epsilon, this average error rate, at any location in the circuit. This might not be exactly true. Unless it's approximately true, one of these plots doesn't really say very much. And so the idea here is we have one of these circuits. It's just like a grid, and errors occur with this probability epsilon at any location independently. So if this actually was the case, you had one of these error models, then what circuits you can run is actually really simple. Because if circuits are smaller, then a lot smaller than 1 over epsilon, and by its size, I mean its width times its depth, or basically just the number of gates it contains. If it's a lot smaller than 1 over epsilon, then you're going to be able to run that circuit successfully because the probability of error is negligible. If it's a lot larger than 1 over epsilon, then it is going to almost certainly fail because the probability of there being an error is basically 1. And so you get this divide into a region of circuit shape space. So this is width times depth plot here, where the circuits all the circuits of these shapes will run with a high success rate. And outside that region, all the circuits will run with a very low success rate, so you can't actually run those circuits. And in actuality, this would be an exponential decay. There's not just a sharp cutoff. But the problem is that real processors really aren't accurately described by a single error rate, as I'm sure most people here are perfectly aware. So there are many, many ways in which this isn't true. I'm just going to give you a couple of really simple examples just to be illustrative. And so one possibility is this crosstalk or just non-uniform qubit error rates, in which case, as you increase the widths of your circuit, you have to add in worse qubits. And so what happens is your performance drops off more quickly as you increase the width than you expect it to if there really was just an error rate for the whole device. A different kind of effect you can have, which is also pretty much ubiquitous, is you can have different 1 and 2 qubit gate error rates. And so perhaps the 1 qubit gates have really low error rates, that's often true, and the 2 qubit error rates are much worse. That's really the case in most devices currently. And then what will happen is as you increase the density of the 2 qubit gates in the circuits, you're not going to be able to perform as large a circuit without almost certainly getting failure. So these are really just illustrative examples. What they're telling you is that predicting a processor's capability is really more complicated than just measuring its error rate because it doesn't have an error rate. And so once we realize this, then you need to think about how can you actually go about learning about what errors are going on in a device. So there's 2 general kind of ways to go about doing this. One of them is model-based characterization. This includes techniques like gate set tomography, which is something we work on at the QPL, process tomography, which is a simpler version of this, cycle benchmarking, that's something from Joseph Emerson's quantum benchmark company, Howie noise estimation from Steve Thamir's group. There's a long list of different types of model-based characterization. And all of these techniques have the same general outline. So how they work, you start with some kind of parameterized error model for the device. There's some parameters in it that you don't know that tell you about the errors. So in the case of tomography, this is process matrices that describe the gates. And essentially, you have a bunch of matrices where you don't know what the parameters are in them. So essentially, you need to fill in the numbers in this matrix that describes your device. And so what you do is there'll be some circuits that you run, you get data, and then you estimate the model parameters from this data, just using standard statistical inference techniques. And then you get a filled out error model. So for example, in the case of the process matrices, you filled in all the numbers. And so this is a predictive error model under which you can simulate any circuit. So you have some circuit you're interested in, perhaps you want to run this QAOA circuit, you can simulate that under the error model, and get out a prediction for how that circuit is going to perform. And this is really great in principle. Like, this is a first principle is exactly what you want to be doing. The problem is it's actually really challenging to scale to many qubits. This is the famous exponential scaling problem of tomography. And it's not necessarily impossible to scale it to many qubits. This is part of what we do at the QPL, is trying to push this as far as possible. But it's certainly challenging. And there's many different reasons why it's challenging. One simple one is that the most basic parameterized models that you get have an exponentially large number of parameters in them. And so you can't actually estimate that from a reasonable amount of data as you increase the number of qubits. But even if, say, you had already had a really good model for your device, perhaps you have some really brilliant device physicists, they know all about the physics of the device and know exactly what should happen, you still can't necessarily simulate that error model for your circuits of interest, because simulating quantum systems is very hard. So you can't even necessarily simulate the circuit you're interested in without any errors. And so even that part of it is challenging. There's many different components that make scaling up model-based characterization a real challenge. The other general methodology for going about learning about what a quantum computer can do is benchmarking. This is a more heuristic and ad hoc kind of way of doing things but could also potentially scale a lot better. So the general framework is you have some benchmarking circuits which you run on your quantum computer, and then you get some kind of score via some kind of simple data processing, and from that you do some heuristic performance predictions. And so this talk is about new scalable holistic benchmarking techniques. And so there are already a lot of very nice benchmarking techniques out there, as I'm sure most people here are aware. Here's just a few examples of some of the most popular techniques. Randomized benchmarking is used by pretty much every experimental group in the world. It's one of the just de facto standard techniques, which involves running particular types of random circuits and looking at how their success decays as the sequence gets longer. Running algorithms is also a commonly used technique for testing how good people's devices are. So you just run a small instance of some algorithm and see how well it does. Quantum volume is a very popular recent technique from IBM that involves running a certain class of random circuits, and then you extract this number that they call the quantum volume. Cross-entropy benchmarking is another really popular technique, which is what Google used to benchmark their Sycamore device and was a key part of their demonstration of quantum supremacy. And there's plenty of other techniques too, so if I didn't mention your favorite one, then sorry. So do we really actually need any more benchmarking techniques? So I'm going to argue that we do, because current techniques have a few limitations. I'm just going to highlight a couple of them here that I think are the most important ones. So the first of these is that most methods that currently exist just don't scale well with the number of qubits. So this happens for a few different reasons. So RB is often thought of as being scalable. That's often how it's advertised, but it doesn't actually scale that well because it requires gate combination. So Clifford RB is the most widely used technique, and it involves running. So if you want to benchmark n qubits, you sample circuits containing uniformly random n qubit Clifford gates. And the problem with this is that an n qubit Clifford gate is actually an object that has to be compiled into lots and lots of 1 and 2 qubit gates on the device. And this scales roughly quadratically with the number of qubits. And so what ends up happening is to run even the shortest circuit in this benchmarking technique. As your number of qubits increases, this circuit just becomes absolutely huge, and even a really good device just can't run it. So there hasn't been experiments that implement more than 3 qubit Clifford randomized benchmarking for this reason. And this is illustrated by this plot of Clifford RB decays as you vary the number of qubits. So this was a simulation with like 1% error, I think. And as you increase the number of qubits, what you see is that the success probability you get out of these circuits from the shortest circuit, which here is noted by sequence length 0, just drops down precipitously as you increase the number of qubits, and then you're basically just getting nothing out. Even though this is actually a pretty good device, this simulated device, it has 1% error. That's quite good. Comparatively, quantum volume, cross-entropy benchmarking, and algorithm-based benchmarks, and some others too, they require exponentially expensive classical computations because you can't actually efficiently simulate the circuits. The reason for this is the general way that benchmarking typically works is that you run some set of circuits on your device, and then you also simulate running that circuit, and then you compare the output to score how well your device did. And the problem is if you can't do that simulation on your classical computer efficiently, you can't do this. And that's in fact one of the ways in which they demonstrated quantum supremacy. They use the same circuits from the benchmarking to actually demonstrate the quantity supremacy, because they can't do the simulation. Then there's another more subtle limitation of current methods, which is that they pretty much all use random disordered circuits. Just as the case with cross-entropy benchmarking and quantum volume and randomized benchmarking. So the circuits they run have independently sampled layers. And I'm going to come back to why this is a severe limitation of current methods later on. So hopefully I persuaded you that we do need new benchmarking methods. So before we go about trying to develop one, you need to think about what characteristics you actually want of a benchmarking technique. So the first thing that I think we want is that we want it to be scalable. So in order to be able to scale this to any number of qubits, we need a couple of things. So we need to be able to have shallow circuits. Because imagine someone comes to you and says they want to test 100 qubits, and then you say to them, well, you need to run these 10,000 depth circuits. Then they're going to say that's just not going to work, because that would require 1 million gates. And even with a very good device, they're very unlikely to be able to implement 1 million gates without an error. They'd have to have 10 to the minus 6 error rates, which is just not feasible. But we want to be able to benchmark 100 qubits that say have 0.5% or 0.1% error. That's an okay device. We want to test it. That would be a spectacular device for current standards. And so we need to be able to have shallow circuits for any number of qubits so that we can benchmark any number of qubits. And the next property we need is we need that every benchmarking circuit to be efficiently verifiable, so that after someone's run the circuits, we can actually tell them how well they did. Because if someone runs the experiment and then you say you're going to need 10,000 years to actually assess how well they did, they're not going to be very impressed with that. And that's what would happen if you did cross-entropy benchmarking on 54 qubits. But we don't just want this to be scalable, because we could just come up with a really trivial benchmark that was scalable. I could just tell you to initialize your qubits and then measure them. That scales fine, but it doesn't actually tell you very much about the device. What we also want is we want the benchmark to be representative. So we want performance on the benchmark to reflect performance on some applications, or perhaps a specific user-specified application. So if someone comes to you and says, I want to run QAOA, can this device do it? We want to be able to have a benchmark that can tell them roughly whether it's going to be able to run QAOA or not successfully. So we think we have a solution, a new benchmarking technique that actually satisfies these criteria. And what it is a method to map any circuit to a set of benchmarking circuits. And this set of circuits has two properties. First property is that every circuit in the set is efficiently verifiable. And the next property is that a process's performance on circuits sampled from this set is representative of how well your device will perform on the original circuit. And so this isn't exactly the same as the criteria I had in the previous slide. So let's see why we satisfy them. So we can have really shallow circuits, because that will be satisfiable by choosing the circuit from which you construct the benchmark. And then the next criteria of being efficiently verifiable, well, I've already stated that as one of my two properties. And then we want them to be representative, and we're going to satisfy this because I've said that the suite that you get from a circuit is representative of how well you can perform the circuit you started with. And so if you come to me with a set of circuits that are representative of something you want to do, then my benchmark will be representative of that. So say you want to run QAOA and you give me some QAOA circuits, and my benchmark will tell you how well you can perform those QAOA circuits. So our technique is actually built on a really obvious idea that has some limitations, which is just time reversal. So you start with this just generic circuit that you're given that we want to send to a benchmark. And what we do is we construct a circuit that consists just of that original circuit, and then that circuit in the reverse order with each gate replaced with its inverse. And so what that means is that if you implemented this perfectly, your overall computation, even if the original circuit is very complex, does nothing at all, because you can see there's two central layers that cancel each other, one's the inverse of the other, and so on. So if you do this perfectly, it just collapses down to doing nothing at all. And so you input your zeros bit string, you should get it back out. If you don't, you know there's been an error. And this really isn't a new idea at all. So this is a Loschner echo, which comes from the 19th century. It was a counterexample to the second law of thermodynamics, I think. And a similar idea is in Joseph Emerson's original RB paper, which is one of the foundations for benchmarking quantum computers. And this idea has been explored various times since then as well. But it's always been essentially discarded as not a very good idea, because this circuit, the performance on it is really not actually representative of how well you can how well you can perform this original circuit C. And the reason for that is what you're doing is you're just testing whether you can undo an evolution, not whether you actually did the correct evolution. So you can see this by a really extreme example. Imagine someone just failed to turn their quantum computer on, and so you just always get the 0-bit string out when you query it. And this, although it's a pretty extreme example, these sorts of things do happen, like there's catastrophic failures in like the control systems of quantum computers. That's not unusual. And in this case, what we would get is we would always get out the all zeros bit string, and we would say that you have a brilliant device, even though it does nothing at all. And so what we're seeing here is that there's certain types of errors we're not sensitive to. And in fact, there's a large class of reversible errors that we're not sensitive to with this kind of circuit. Because really all we're doing is testing whether we can undo an evolution, which is really not the same thing as testing whether you did the correct evolution or not. But it turns out you can actually fix this methodology with some pretty straightforward alterations. So what we do is we insert randomized state preparation and measurement circuits at the start and at the end of this circuit that we create. An important part of this, these inserted circuits need to be small so that we're not actually blowing up the size of this and losing scalability. And in fact, we just stick to single qubit circuits. And the reason that we insert these is that the original circuit, all you ever do is input the 0 state and then measure it in the computational basis, but perhaps you actually want to know how that circuit performs as part of a larger circuit, so in a more general context. And by randomizing which states we put in and which measurements we perform, this allows us to actually probe how well it runs in different contexts, so how well it will work as a subroutine. And the particular randomization we use means that we're sensitive to a particular property, which is process fidelity. Then in the center of the circuit, which this is perhaps the most important thing, we insert a central random circuit. And again, we need this to scale well, so we only insert single qubit gates on each qubit. And the reason that we do this is if we do this in a particular way, it means that errors cannot systematically cancel on the circuit and the reverse of that circuit. So we remove this really crucial problem with the just standard Loschmidt echo that errors can cancel systematically. And finally, we do some minor tweaks to the inversion layers. We call them quasi-inversions in order to account for this central randomized circuit so that this entire circuit still collapses down to something really simple. We make it always collapse down to some kind of bit flips so that there's always a single bit string that you should get out. So you look to see whether you get that bit string, and if you don't, you know there's an error. So on the previous slide, I didn't actually give you a concrete construction of how to do this. So I'm now going to tell you quickly about the details of how this works for Clifford circuits, because that case is a bit simpler, and because all of the experiments we did only use Clifford circuits, which is why I'm going to be telling you about the rest of the talk. But this works on more general circuits, including universal gate sets. So for Clifford circuits, what we do is at the start and end of the circuit, we implement a uniformly random single qubit Clifford gate on each qubit. And what a random Clifford gate does is essentially it randomizes over the different Pauli axes, and this randomizes the direction of errors, which gives you a form of basically uniform sensitivity across different types of errors. So anyone who's familiar with the theory of randomized benchmarking will know this is a form of group twirling. But crucially, we're doing this locally, so it scales. Then in the middle of the circuit, what we do is we insert a uniformly random Pauli gate on each qubit. And because the circuit is Clifford, what that means is that U Pauli, U inverse must equal some other Pauli. So the entire circuit just equals a Pauli, which means it just does bit flips, which we can really efficiently calculate. So you can calculate what one of these circuits does for like tens of thousands of qubits in seconds using, for example, Scott Aronson's CHP code. It's a scales quadratically the number of qubits, maybe n log n. So circuit mirroring, which is what we call this technique, is really very general. It's a really general tool for creating benchmarks. But to actually have a specific benchmark, we need to insert some kind of circuits into this framework. So one natural and interesting thing to do is to insert algorithm-based circuits to create a benchmark that is reflective of how you can perform a particular algorithm, but that also really scales well with a number of qubits. So this is ongoing research. So I'm not going to be telling you about this today, and in particular, to really investigate interesting algorithms, we need to do this with non-Clifford circuits. And so there's a few extra complications there, which I'm not going to be talking about today. In the remainder of this talk, I'm going to tell you about randomized and structured circuits. These are very similar to RB circuits. We insert random layers. And I'm also going to talk about benchmarks based on repetitive circuits. And I'll explain what they are a bit later on. So for most of the rest of the talk, I'm going to be telling you about some experimental results. So we've actually done these benchmarks. This will help show why we think these are really interesting benchmarks and show you things you can learn from them. So we did 2 different experiments. I'm going to tell you about the first one now. So what we did is we benchmarked 12 different publicly accessible quantum computers. And there's a lot of data on this slide. So I'm going to step through everything that's here before even talking about what you can learn from this. And so this benchmark was in randomized mirror circuits. So that's the class of benchmarking circuits shown in B. If you're not particularly familiar with benchmarking, just think of these as circuits with random gates put into them. So there's 12 different processors here. So the name above each plot tells you which processors we're looking at, and it also shows you the schematic of that device. So there's 9 from IBM and 3 from Rigetti, because these are what we had available to us. And they go up to the largest one, 16 qubits. And then what we did is we ran varied width and depth randomized mirror circuits. So each different plot, you can see what the axes are. The horizontal axis is circuit depth. So you can see we varied the depth of the circuits. So for example, if you look at IBM Yorktown, we've run circuit at depth 0, 4, 8, 12, and so on. This is a form of exponential spacing. And then the vertical axis is circuit width. So this is the number of qubits we're benchmarking. So for example, on IBM Q Melbourne, the one at the top, we do 1, 2, 4, 8, and 14 qubits. This is the circuit width, and we have exponential spacing up to the size of the device, because it's a 14 qubit device. And this general framework for doing this, sweeping out the different widths and depths of circuits and doing these kind of plots, this is known as volumetric benchmarking, which was developed by Robin and Kevin at the QPR. And so what are we actually plotting? So each width and depth pair, so that's what the axes show. And what we did is we sampled 40 randomized mirror circuits, and then we run each one 10,000 times. And then we summarize how well it performed via polarization. So what we do is we see how many times we get the correct bit string. So each of these circuits, there's some bit string it should always output. We look to see how often it did. So that's an estimate of its success probability. And then we rescale this to what we call the polarization, which basically just removes a number of qubits dependent factor. This is essentially the contribution just from the maximally mixed state, or you can think of it as the contribution from just getting a random bit string out. Essentially, this is just to make the plots be more convenient to look at, so that we don't have a circuit width dependent factor that we kind of have to carry around in our heads with us. But if you just think of everything as success probability, it's not really going to make much difference to anything. And then finally, what specifically we're actually plotting. So what we do is each of these individual squares, you can see, is made up of 3 different squares. So the central square, the smallest one, is the maximum polarization over the 40 circuits. Then the next square is the mean over all those 40 polarizations. And then the outer square is the minimum polarization over those 40. So essentially what we're doing is very concisely plotting information about the distribution over the polarizations, or basically success probabilities, for all these 40 different circuits. And as well as actually just plotting that data, we also show thresholds or frontiers at which these 3 different statistics drop below a threshold value, which we set to 1 over E, as that has some kind of convenient properties, but it's not of huge importance what the threshold is. So that's the green, black, and red lines. They correspond to the frontier at which your maximum, mean, and minimum polarization drop below this threshold.
So there is from Vincent Pascuzzi. We have a quick question, I guess, from Vincent.
Sorry, could you say that again? My volume was kind of low.
Sorry, I think we have a question from Vincent. He has his hand up.
Go for it.
For the circuit width, how do you choose the qubits in each of these selections for the width?
So for this experiment, what we did is we selected multiple sets of each width, did benchmarking on those, and then we selected which set was the best. So we selected the one that would give you the furthest frontier for the black line.
Okay.
And in the later, so yeah, that's not explained in here. And in the later experiments, I don't explain what we did either. In that case, what we do is we use the calibration data for the devices, and we picked the best region according to the calibration data and just benchmarked a single region of each
Great.
size.
Thank you very much.
But yeah, there's lots of different ways you could do this. So there's a lot of different information here. You can learn a lot of stuff about these devices. For example, you can compare different devices, see how one compares to another. So in the case of, say, IBM Q Tenerife, which is one of their old 5-qubit devices, you can see it's pretty much unambiguously worse than all their more recent devices that are clearly performing better. All the frontiers are higher up. They're all like darker blue, the newer devices. So let's say IBM Q, like Arens, Essex, Burlington, Vigo, they're all a newer design, and you can see they're all a lot better than IBM Q Tenerife, which is an old device. So this is a really easy at-a-glance way to compare these devices. You can also learn a lot about an individual device, and you can learn things about what's going on with that. I'm just going to focus on a particular feature that you can learn in order to not get bogged down in too many different details. And so that is that what we can see is that mean performance on randomized circuits is not always predictive. So what I'm saying by that, is that if you look at a fixed shape random circuit, what you see is that there's a large variance for some devices in how well the different circuits perform. So here I've just focused on 2 devices. One of them is IBM Q Vigo. And what you actually see is a low variance in this case. But so if you look at each of the squares, all the different blues are a similar color, and you can see that the red, black, and green lines are very close together. So what this is saying is that out of the 40 circuits we ran, they're all performing very similarly to each other. And so in that case, the mean over those, the mean performance of those circuits is a pretty good predictor of how the typical random circuit will perform. If I pick something from that ensemble, it's pretty likely that it's going to perform pretty close to the mean. If instead you look at Rigetti Aspen 6, you can actually see that there's a really large variation. So there's very different colors of blue in each of the squares. The red, the green, and the black are far away from each other. And it's not really surprising that you might have large variation for some devices, but this is actually a kind of important point to realize that this happens, because many performance metrics you get out of things like RB, cross-entry benchmark, and quantum volume, they summarize performance with a metric that really is just related to a mean over random circuits. And so what these kind of results are telling you is that kind of metric often won't accurately predict how any individual circuit will perform, even a circuit drawn from the same distribution. And someone giving you a statement about expectation values of how well your circuit's going to perform really isn't that useful generally. If you want to run a specific circuit, you care how well that circuit is going to run. And if you want to know things like that, you really can't be using metrics based on averages over random circuits. And so what does that actually tell us about the device when we see this large variation in performance of equal shaped circuits? So what this means is there's structure in the errors. So you cannot actually get this if you have that simple IID depolarizing model where you just have an error rate that I talked about at the start. And there's many different types of structure. Anything that's a deviation from this IID depolarization would be something we'd call a structured error. So something very simple is just that each gate has a different error rate. That's pretty trivial and easy to model. But there's lots of many more complex types of structure, so unitary and calibration errors, which are fairly intuitive, but they're actually very hard to deal with in terms of modeling. There's biostochastic noise, there's crosstalk, you can have drift, you can have all sorts of subtle effects that are a form of structure to your errors. And this is important because structured errors can be catastrophically amplified if a circuit has some kind of matching structure in a heuristic sense. So for example, if you have Z coherent over-rotation errors and you have a circuit that spends a long time in the Z basis, so you spend a lot of time idling, that can add up coherently, and that's a very different effect to stochastic noise. And
we have another question for you as well.
Yeah,
we have another quick question for you. We have another question for you from Costin.
Great.
Oh, hey, thank you. So I have a question. This methodology, you are saying that whatever people are doing is not good enough to predict the performance, but seems to me that we are more interested in predicting the order of performance. So if I give you 2 circuits, I need to know which one is better, not necessarily how good is each.
As in you saying that people want to know which device is better, not
No, yes. So you say I have a fidelity number, yeah? And then I run a circuit on one device based on this fidelity number. I run the same circuit on a different device based on this fidelity. We cannot say the final result or whatever the final quality of the result is. We cannot assign a metric to it because fidelity doesn't characterize the system. But if fidelity characterizes the sort of the quality of the solution between the two systems, I think isn't that a lot of information that we can already use?
So certainly mean performance is a useful metric. I'm not saying it isn't a useful metric, but fidelity doesn't give you a very strong bound at all on how a specific circuit will perform. So if I have a device with a lower fidelity, average fidelity of its gates than yours, it might perform better on certain circuits. Because if you have strongly coherent errors, I might be running a circuit that has, say, dynamical decoupling in it that actually cancels the errors that one device happens to have. So just because you know one device has a higher fidelity, there's no guarantee that it's going to be better at something specific that you want to do. Now, often that's not going to be the case with real devices, right? Because it depends on the kind of errors. If you're dominated by stochastic noise, so particularly if you just have like IID depolarization, then fidelity tells you everything, right? So you don't need anything else, and you can just compare devices based on fidelity. But I think most devices just aren't like that. They don't just have stochastic noise. Hopefully they will in the future.
Okay, thank you.
So structured errors, one of the problems is that, sorry, somebody else wanted to ask a question?
No, I think we're good. Let's keep going.
Okay. Structured errors can be catastrophically amplified by circuits that have a similar structure to them in a heuristic sense. And so this kind of makes it clear why random circuits are not good as your only method for benchmarking, because they only contain structure by chance. So they're really going to be a very inefficient probe for structured errors. In contrast, something like a periodic circuit can amplify structured errors. So here is a picture of what I mean by a periodic circuit. You have some kind of short sequence of gate layers, and you repeat that many times. There's many different kinds of structure. We're calling this a periodic circuit. So in order to look at how this effect actually manifests in current devices and to try and show that you really do need to be using structured circuits in your benchmarking, we ran similar periodic and random mirror circuits. I'm not going to tell you the details of exactly how they're constructed, except to say that they're made to be as similar as possible, except for one type is periodic, the other type is randomized. And so, for example, they have a fixed 2-qubit gate density across the two different types of circuit. So I'm just going to show you some experimental results from 3 different devices. We ran this on 8 and saw very similar results for all of them. So what we're plotting here is the worst case performance of the periodic circuits and the worst case performance of the random circuits for one of these volumetric benchmarking plots. So what we did is there's 40 circuits of each type, ran at each width and depth. We picked the one that has the worst polarization and we're plotting that. And so for each device, we're plotting both the periodic and the random case. So the periodic circuits are the outer squares, and then the random circuits are the inner squares. And again, we're plotting this polarization quantity. And what you can see is that this polarization in the worst case drops off much more quickly for the periodic circuits than for the random circuits. So you can see the outer squares, they drop off to red much more quickly than the inner squares. And this is really important because most algorithmic circuits are highly structured. By the nature of being an algorithm, it has to contain structure for pretty much every algorithm. And so what this is telling you is that randomized benchmarks really are not that likely to predict a process's performance on interesting applications if you have highly structured errors. Now, if you have a highly structured circuit, it could perform a lot better than predicted by a randomized benchmark, but it could also perform a lot worse, as being shown here. So you might wonder, right at the start of the talk, I said that device quality is often summarized by error rates. So there's this really simple way of summarizing something just by one error rate. But I think most people know that in practice, what actually happens is there's a lot of different error rates that are measured. So for example, this is what you get if you're using one of the IBM devices. It's an out-of-date screenshot, but it shows like different error rates for each of the different qubits. There's readout error rates for each qubit. There's a 2-qubit gate error rate for each different 2-qubit gate. It's the kind of thing you get when you access like Rigetti and IBM. It's the kind of thing that people publish in their papers. And you might wonder, can I just add up these error rates? And will that just tell me how well the different circuits perform? So you just add up the error rate for each gate in a circuit, and will that predict performance? Because this could perhaps just explain what's going on here. And rather than adding up, we use the depolarizing model, which is what adding up to basically an approximation to. And so we did this. So we use the manufacturer's error rates. You get these when you run these devices to predict the success probability of every single circuit. And then we compare to what we actually see. So if you look at column B, this is the prediction from the error rates for exactly the same thing as we're seeing in A. So this is the prediction for the worst case over the random and the periodic circuits of each size. And what we're seeing is the predictions. For one thing, they predict that the periodic and the random circuits should perform about as well as each other. And that's because the prediction is based on this stochastic noise model, which is essentially what's implicit in error rates. So they can't actually reveal that we're going to get this really large difference. And also we're seeing that the predictions are over optimistic for the same reason that they can't model the structure in the errors. And if we look at the column C, what we see here is the scatter plot for all the different circuits that we ran of the predicted failure probability versus the observed failure probability. And what we're seeing is both that the error rates are over optimistic, which is a sign of emergent errors like crosstalk, which is not really all that surprising, although it's interesting to actually have these benchmarks to see that that's happening. And we're also seeing this large spread vertically, which is showing that there's actually a lot of structure there. So there's a lot of variance in the performance for the same, roughly the same predicted value due to these structured errors. And this just cannot be modeled by these error rates. And one thing I'm not showing here is that we also estimated the error rates from the data that we had, because you could just say, well, they've got the error rates wrong and things have drifted. So we got the best estimate of the error rates from the data, did maximum likelihood estimation of the error rates, and those still can't predict these results because there really is structure in these errors. So going back to kind of how we started the talk, I was saying that we really wanted a way to measure capabilities, kind of communicate this. So we'd like to be able to both give a reflection, like an accurate reflection of how good a device is, but also something that can be digested either by someone who's a non-expert who just wants to run their quantum algorithm on a device, or by experts who just want to have a glance at something and see what's going on. I'm not trying to do something that's better than these error rates, but it's still digestible. And so we came up with what we call capability region and plots. There's various different types of these plots that you can make. So here what I'm showing is the region. The green region is the region in which every circuit of that shape ran successfully in at least 2/3 of the run. So the success probability of at least 2/3. And the black region is the prediction of what there should be according to the error rates. And so we're seeing that if you just use the error rates, you would have a very over-optimistic prediction for some of these devices. We also think this is a reasonably intuitive way to represent what you can do with the devices. And in particular, because we ran a fairly large range of circuits, so the benchmarks contain both these random disordered circuits and also these highly periodic circuits, we think that these prediction regions are going to be reasonably representative of the circuits you might want to run. So if you come to me with a circuit and I can see where it's in the green region, I'd say there's a decent chance that might actually run on the device. If it's well outside it, it's clear it's not going to. And we're seeing here that the observed capability is really a lot worse than predicted. And there's various different types of capability region that we can create that have different levels of information in them. So what this is showing is the region, the green region is where all the circuits succeeded. The orange region is where some of them did, and the white region is where none of them did. So if you came to me with a circuit that had a shape that was in the white region, I'd say you're pretty much guaranteed that it's not going to work. And if it's in the orange region, it's like, well, maybe you might want to give it a go. And if it's in the green region, then there's a pretty good chance it's going to work. So these kind of plots, I think, will be very useful when someone's deciding whether they should even consider trying to, say, run their QAOA algorithm on one of these devices. I mean, currently the answer is obviously no, you can't do anything useful with these devices. But hopefully in a few years, that's going to change. And we'd like to be able to make these plots for devices that perhaps you can do something useful with. And then people are going to be able to assess, can I run this algorithm or this circuit on that device? And I think an important point to make here, there's really a lot of open questions about how to extract all the useful information that there is in this data. So these benchmarks, you get a lot of data, there's a lot of information there, you can learn a lot, and there's a lot of work to do in how to both extract all the information and also how to present it in a way that is actually intuitive and useful. So I'm just going to briefly tell you about some additional useful data analysis you can do with randomized mirror circuits. So I have said you really shouldn't just be doing randomized benchmarks, but randomized benchmarks do have some nice features, and in particular, it allows you to estimate an average gate error rate or average infidelity. And it turns out randomized mirror circuits can actually be used as one of these traditional RB protocols, which is a general, there's a large suite of these protocols called randomized benchmarking. And the general idea of them is you want to estimate the average gate error rate or the infidelity. And it turns out randomized mirror circuits is a scalable way to do this. So if we do some simple data processing, we don't quite just look at the success probability. We then fit that to an exponential as the length of the circuits increase. Then we can estimate an average gate error rate. And by gate here, what I'm really referring to is an n-qubit circuit layer. And what's really cool about this, it scales to hundreds or thousands of qubits. This is really a huge improvement on traditional RB. So Clifford RB, you can only really go out to say about 3 qubits with current devices. And direct RB, which is a method that we developed that's more scalable than Clifford RB, but we still only managed to go out to about 5 qubits. This can really go out to hundreds or thousands of qubits. So what we're showing in the bottom left is the error rates we extracted from this data I was showing you earlier on IBM Melbourne. What we can actually do is extract the average fidelity of their circuit layers as you vary the number of qubits in them. We can also compare that to the prediction, and this is a useful way to quantify the immersion errors, so particularly crosstalk going on in their device. And I've claimed it's scalable, so I'm just going to briefly show you a simulation of a 225 qubit lattice. So we simulated this with long-range 2-qubit gate crosstalk, because this is an error model where you really do need to be running large circuits to actually be able to see it. So we simulated both with the crosstalk model and without the crosstalk model. And so observed, it refers to the crosstalk model, and predicted is the crosstalk-free model. And it's called predicted in this plot because this is what you would think is going to happen if you did local RB on each of the qubits and then predicted what would happen when you ran bigger circuits. And so the left-hand side is just showing you one of these volumetric benchmark plots, which is just a simple way to represent the data concisely. But what we're doing to get out these error rates is we get these like classic RB decay curves, and we fit them to an exponential. So for each number of qubits we have, so 9 qubits as highlighted there, we fit the data to an exponential decay. We get out an error rate, and then on the right-hand side, we're plotting this as you vary the number of qubits. And this is, I think, essentially a really powerful tool for seeing what kind of errors are going on. So for example, with the crosstalk errors, you can see you get this kind of characteristic quadratic growth to start with because there's because of the interactions between the qubits. And I think we're running a little bit short on time, so I might skip the results for applying this also to another IBM device. I'll just quickly say that one of the nice things you can do here is, so we ran, this is reanalyzing the data from the very first experiments I showed you in this talk, where we were benchmarking multiple different regions. And what you can get out is these nice plots of the error rate over the different regions of the device. So that's what's being shown on the right-hand side here. The device is at the bottom, and then you can show how the error rate is changing with the different regions as you increase the number of qubits and as you go to different parts of the device. And we can do this because the technique is so scalable. So here we're managing to actually get out the error rate, even though when we benchmark all 16 qubits, it has a 35% error rate. So there's no possible way you could do other RB techniques here. So just to quickly summarize, I think we're getting into the kind of time when people really want to know what programs the device is capable of running. So there's people outside of our field getting into it, and they're really interested in running algorithms, and they want to know, can this device do it or not? And we really need concise ways of actually measuring what devices can do and then actually communicating it to people. And so we've started along this line trying to get towards techniques that can do this. And to do this, we've introduced this scalable benchmarking technique called mirror circuit benchmarks that we think is a reasonable attempt at measuring a processor's capability. One of the things these experiments are showing is that performance on random circuits is not going to be predictive of performance on non-random circuits, at least not until devices have been so improved that really all you're left with is basic IID depolarizing noise. But we think that these mirror circuit benchmarks are hopefully going to be a nice foundation to build scalable and targeted benchmarks that can predict how well a particular application will run. There's really a lot of open questions about how to do this. We've not gone through all the details of actually building an application-specific benchmark. We haven't actually run any experiments that use these non-Clifford circuits in the benchmarks. There's a lot of extra work to do in terms of how we can learn everything possible from the data analysis and so on. So I think there's a lot of exciting open questions here. So thanks for your attention. And also quick thanks to IBM and Rigetti for really giving us access to these really great platforms that allow us to learn a lot. And if this work is mostly in this archive paper, and I'd be very happy to talk to you more if you wanted to get in contact with me, and obviously you're welcome to ask questions. Thanks.
Okay, thank you, Tim. Let's clap for our host for a great talk. Okay, so we'll open up the floor for questions. I know Robert Cook has his hand up, so maybe we'll go to Robert.
Yeah, I was curious about if you could be a little bit more specific on what you mean by crosstalk. Does that mean like if qubit 1 gets rotation by 90 degrees, does qubit, his neighbor, get rotated by like 5 degrees, or is there something more or less specific you can say about that?
So most of the time when I was talking about crosstalk, I was meaning in a very generic sense that crosstalk is just when you have unwanted interactions or you are doing unwanted driving of other qubits. So I was meaning in a very generic sense. In this specific simulation that I ran, this involves essentially, in order to make this simulation scalable, it's using just a Pauli noise simulator. And so what's going on is that when you apply a 2-qubit gate to a pair of qubits, and all the other qubits increase their depolarizing rate, but with a exponential drop-off with the distance from that qubit on the lattice. So it's kind of like a toy error model for something that's like vaguely realistic. It's not meant to be. It's meant to be mostly a proof of principle of the kind of thing this can detect rather than truly representative of anything real.
Thanks.
I have also I have a question. You mentioned at the end that you say that there is work to characterize a non-Clifford gate, and I wonder, like, what is one of the direction to apply what you did for a non-Clifford gate?
So I have a general technique for applying this mirror circuit benchmarking method to non-Clifford gates, which works for gate sets that say involve, like the simplest case where it works is any Clifford gates plus arbitrary Z rotations. So I have a technique for this. It hasn't been tested in experiments, and that can always throw up interesting results you weren't expecting. The theory is mostly worked out, but could do with a bit more like finessing. I haven't run any simulations, so like there is. I feel like it's the tools are there, but you never know what's going to happen when you're actually trying to do it, right? There could be some flaws in it. There maybe needs to be some changes to the technique. Maybe, yeah. So it's at that stage where I think everything's good about it, but we'll see in practice. So.
Okay, thank you.
We'll go to Lin for the next question.
Thank you for the very nice talk. I have a question, which is the quantum volume and cross entropy benchmark also has this kind of classical hardness aspects in it, right? And which means that if you want to, you can use it to show that the quantum computer beats the classical computers. So does your benchmark have something along this aspect, or this is deliberately avoided?
Right, so the actual benchmarks themselves are trivial to fake on a classical computer, right? Because I know what bit string it should output, so you can just fake it, right?
Yeah.
That's also true with quantum volume and cross-entry benchmarking, because in the regime where you can actually use them as a benchmark, you have to be able to do forward simulation, and so you can predict what it should do. the question about, so I guess one way to interpret the question, I don't know if this is what you mean or not, but can I use these benchmarks to essentially guarantee that some circuits that should give me a quantum advantage are performing well enough?
Right.
And I would say that,
yeah,
that is true, but it requires assumptions, which is intrinsically necessary, right? Because if you're going to infer how well some other circuit runs from how well this circuit runs, there's necessarily some assumption about the relationship between the errors in this circuit and that circuit. The exact assumptions are a little subtle, but mostly the case is just that essentially we are measuring more or less the process fidelity of how well you can run that original circuit that you constructed the benchmark from. And the process fidelity gives you like formal guarantees about output distribution, about the output distribution. The thing it actually formally bounds in a fairly tight way is the classical fidelity of the output distribution. And that is generally not a metric people use that often. We use fidelity so much, I think, largely just because it's convenient, right? We can often measure things that are based on fidelity. The fidelity of a classical probability distribution is not so like intuitive, I think. We can then bound the TBD, which is often the total variational distance, which is often the kind of quantity that people are more interested in. So this is a roundabout way to say, yes, we can give some kind of guarantees, but they're intrinsically going to be based on some level of assumption. And whether this is, there's probably other benchmarking techniques you can use that probably involve different assumptions. And my expectation is probably what we're going to be wanting is a suite of different kind of tools which can take a circuit, turn it into an efficiently verifiable form that then gives you some kind of guarantees on the original circuit, and that each of these different techniques has different like small holes, and that with all of them together, we'll be more confident that this original circuit we're running actually does perform well.
Thanks. So back to my question, is that fair for me to rephrase saying that although the cross entropy benchmark has both the hardness and the benchmark aspect in it, but these two things do not necessarily need to be combined together, especially from a pragmatic perspective. You just generate any number that shows the quantum computer is performing well, that's already very useful.
Right. And you can potentially do some like formal proofs linking that number under some assumptions to some other metric. So for example, what they do in the Google experiments is they, for the very largest, to benchmark the full device, they just remove some of the connections and then say, well, this is doing, we can predict how well this is going. We can do the forward simulation of this to use this as a benchmark. And we have no reason to think that the full circuit, when you add the connections back in, is going to be any harder. So it's a very similar kind of idea of taking a hard circuit, doing something to make it easy to simulate, and then saying, well, the quantum computer doesn't know that I've done this trick to make it easy to simulate, so surely I can do that other circuit just as well.
Okay, thank you.
Okay, other questions for Tim? Maybe I can also ask one. If you go to slide number 32 or so, I was sort of looking at these plots and trying to, the one with this 33, so one more back. Yeah. So this is very interesting, right? So you had sort of predicted regions and things that you actually get in practice. And I was trying to pull out some patterns. And I know in the next one, you said, of course, this with the little spoiler saying there's a lot of information here. It's not so easy to pull out all the details, but do you see patterns emerging? For example, if you subtract these two, right, and go ahead, is there sort of a fingerprint that says, for sure this is a certain type of crosstalk or a certain type of drift, types of patterns emerging?
So in terms of crosstalk, what you tend to see is that the performance drops off more quickly with the width than you expect. That is something you're seeing here, at least in some cases, though, that can just happen because you just have a bad qubit, right? And often, like, these are calibrated once a day. I don't know how much effort they put into calibrating them. Sometimes just one of the qubits just doesn't work very well. So, and their numbers are just inaccurate. So from a single instance, it's not necessarily, you can't necessarily infer everything you might want to from this. I think if we did a more comprehensive set of experiments, you can infer more about what each of these patterns is telling you. In the case where things drop off more quickly with depth than you expect, that's pretty clearly a sign of coherent errors in most cases. I mean, it can be due to other things, but that is the most physically likely, and this is the signature of coherent errors. So that's almost certainly what's happening when you get that drop off. In terms of drift, you can see that we actually ran multiple passes with this experiment, and you can then compare how this looks as you so you run it once, then you run it again, and so on. You can look what's changing, and so you can see how much drift's going on. And so yeah, you can use these kind of analyses to learn something kind of high level about the drift going on in the system as well.
Yeah, in fact, some of them I was curious if it also reflects a little bit of the connectivity, because if you look at Aspen 4, right, this thing looks very different. In some sense, the other one has these long tails along both axes, whereas the other one seemed to be sort of a miniaturization of the basic structure.
So in these experiments, we explicitly decided to make connectivity not a factor by having circuits that only contained the native gates of the device. It could still be a factor on a higher level that maybe their connectivity means there's lots of crosstalk. And in fact, with Rigetti Aspen 4, they have catastrophic crosstalk in their device. It's completely.
They have a lot of idle errors.
Right.
Yeah, you may have a lot of idle errors, even though you're not using that particular set of gates.
Right. They also don't do their gates in parallel. So as you increase the width, the circuits also increase dramatically of depth as well.
Okay, very good. Thank you. Other questions for Tim? Okay, going once, going twice. Well, let's join me in thanking our speaker once again for giving us a great talk, and wish everyone a good afternoon. Thank you so much, Tim.
Thanks very much. Thanks.